And when I talked about SchofferNet last time, it's a recurrent neural network. So I realized that maybe you're not familiar with RNN, so I added a few slides on RNN. So a RNN has connections between nodes form a directed graph along a temporal sequence. This allows it to exhibit temporal dynamic behavior. So it can use their internal state, that is memory, to process variable length sequences of inputs. This makes them applicable to tasks such as machine translation and speech recognition. So here's an INN with a recurrent link in the hidden layer. So as it unfolds across time, across different time steps, you have this progression of a transition like this. So this is a video on YouTube. It gives a very good intuition on INN. Since it's a little bit long, I'm not going to play it. I'm just going through the key points. So this is the RNN input at the lower part and output at the upper part. You have the middle layers. So the main idea is that you need to model sequential behavior. So suppose you want to do a translation. What time is it? Obviously, the sequence matters, right? If you mumble the scramble the sequence, what is time is it, or is it time what? So the meaning it gets confusing, right? So it's obviously the time sequence matters. So you you instantiate a RNN, and it takes as input a word and a hidden state, and outputs a output and another hidden state. That is the evolution of the current hidden state at the next time step. And to train the RNN, you can do a backpropagation across time. So as opposed to CNN, where you backpropagate from last layer back all the way to the input layer, RNN you need to backpropagate across time. And there are two special types of RNN which are widely used. One is long short-term memory. One is a gated recurrent unit. So they all have this internal structure in the hidden layer to keep track of memory. So that's the vanilla RNN on the left, where you simply have a simple tiny nonlinearity, and the LSTM, you have a more complex internal structure. In GRU, you have a similar structure. So, and then this video YouTube author has another guide to LSTM and GRU. So yeah, I just briefly show you what it's about. So for example, one application is to identify if user reviews are positive or negative. So using natural language processing, so you have input, output, yeah. So the details are not that important because we're not really studying RNNs in this course. But just to know the difference from CNN is that it has this evolution across time. And because of this, it has internal state. So if you combine CNN with RNN, that is each input and output layers, you plug in a CNN in the middle, so you have a convolutional RNN. So here's one variant, a simple variant of RNN sequence-to-sequence network. Besides LSTM, GRU, you have, for example, you want to do a translation. Input sequence is German, ist as heiß, and output is it hot? So so you take the input sequence, and that's an encoder, and you get a compressed representation of the input sequence, and then you have a decoder that outputs is it hot, the English sentence. So SchauffetNet is a convolutional RNN where it has a feature net, a CNN, for processing render inputs. That is the bird's eye view, not the raw video. It's a mid-to-mid architecture, remember? So, and then it has a agent RNN on the left that outputs a heading, speed, waypoint, agent box heat map at every time step. So and it outputs the predicted agent box where the agent is going to be at the next time step. So as part of the input, past agent locations is a sequence, and its memory. The memory is custom. Is a custom memory, not the memory as the LSTM or GRU. It did not use any of those architectures. So that's the brief review of RNN for the SchauffetNet architecture. You just need to get the basic idea, the high-level concept that RNN is useful for sequence data, videos, natural language, yeah, these kind of sequencing. So if you're just processing individual pictures, you can do a CNN. You don't need RNN. For CNN, you can also process sequence data by stacking multiple inputs together. Say you stack 5 video frames together as input to the CNN convolutional neural network. Then it can also take into account the sequencing among the 5 video frames. But RNA is more natural in processing sequential data. So today, let's continue our exciting journey on imitation learning. Lecture 7, imitation learning. So just to recap, so it's useful when it's easier for an expert to demonstrate the desired behavior rather than to specify a reward function for IR to learn the policy, because the reward function can be very hard to specify. And if you misspecify it, your IR is not going to perform well. So in fact, in industry not in practice, but in industry research, and most research on learning-based autonomous driving is based on some variant of imitation learning. Uh, so including inverse reinforcement learning. IRL essentially calls RL in the inner loop. So it tries to infer a value function and then train the RL agent, and then comes back and modify the learned reward function and in the going in the loop, so that the learned value function is likely to be a much better value function than your hand-crafted value function. So and simpler variants include behavior cloning and direct policy learning. So I just wanted to formalize a little bit these two. So notations. State is typically denoted as S, sometimes X. Action is A, sometimes Y. Policy is pi theta, where theta is the set of parameters. Most likely a set of weights for a deep neural network. You can have a deterministic policy where you have a function pi theta mapping from state to action. Or you may have a stochastic policy where you map from a state to a probability distribution of a set of actions. Maybe 50% chance you go left, 25% chance you go right, 25% chance you go straight. So that's a distribution. That's a stochastic policy. So if you always return a deterministic direction, go north, then that's a deterministic policy. So environment model is this state transition model from current state S, current action A, to next state S prime. If it's known, we can apply model-based methods, including value iteration, policy iteration. If it's unknown, then it's model-free. So what you have learned up to now, Q-learning, actor critique, policy gradient, so they're all model-free. The reason is that models are hard to obtain, especially for complex environments. A rollout is a sequentially execute. You sequentially execute policy pi theta from initial state S0 until time step t. T could be infinity, or could be a limit as to how long your episode is. It produces a trajectory S0, A0, S1, A1, and so on. So P tau theta is a distribution of trajectories induced by a policy. So you repeat until t equals capital T, sample S0 from P0, which is the distribution over initial states. Initialize t equals 1, sample action AT from pi ST minus 1. Suppose it's a stochastic policy. You need to sample the action, and then sample next state ST from applying AT to ST minus 1. So this requires either an environment model, if it's model-based, or a simulator, like Carla, driving simulator, other robotic simulators. So you don't have an explicit model in the form of transition probabilities, but you can write a program to simulate the environment. And then step 4, you go back to step 2 with t incremented by 1 time step. So as you go, as you run these 4 steps, eventually until you come to a time step capital T, you have obtained a trajectory as a sequence of SA tuples. And probability of tau given pi is a distribution of trajectories induced by a policy. So every time you run a policy, you do a lot of sampling. So an environment itself may be non-deterministic. So every time you run the same policy, you may get a different trajectory, a trace, execution trace. So you run it for many times, you get a distribution of trajectories. And you can define a distribution of states induced by a policy, which is defined as average percentage of time you spend in each state. So Pt as given pi is distribution of states at a t's time step. So on average, do you stay in one state for a very long time, or do you stay in every state in about equal amount of time? So yeah, for driving, maybe 90% of the time you're driving straight ahead. So and maybe 10% of the time you're braking hard, and so on. So that's the state distribution. So to compare, the basic behavior cloning is to sample state actions from the expert actions, from the expert execution trace. He's a collection of trajectories, a log. Star means expert. And then you augment, that is to tune the neural network parameters theta so that you minimize the loss function. Loss is defined as the distance between the expert action and your own action. So ideally, you should perform every step exactly the same as the expert, but your pi theta, your policy network, may not be that ideal. So sometimes you have deviations. And the objective of behavior cloning is to mimic the expert as much as possible to minimize the distance between your own action and the expert action. So so direct policy learning is an interactive demonstrator, interactive expert. So you collect demonstrations and then perform supervised learning to train to try to mimic the expert actions, and then you perform rollout and collect demonstrations from expert. So you're asking the expert on demand. So what do I do now? What do I do now? So the expert is ready there, right there, waiting to answer your questions. So inverse IR is to learn a reward function such that you are trying to maximize the expected reward given your policy pi theta. And the sample expectation is over state sampled from the next state distribution. So this argmax expression is a RL problem. So it's maximizing the cumulative reward. And so if you solve the RL problem, you get optimal policy for the reward function R. However, inverse RL wraps an outer loop around the inner RL problem loop. So outer loop says you gotta learn reward function R such that you maximize the cumulative reward. So every time you modify the R function, you rerun the RL algorithm, could be any algorithm, DQN, actor critique, I don't care. Whatever you do, you maximize your reward for that cumulative reward for that value function. And then go back and modify your value function and see if you can get a higher reward and by rerunning the RL. So the assumption is that your learning the reward function is statistically easier than directly learning the policy pi star. So, for example, by policy gradient. So the table compares these three. IRL does not learn policy directly. Behavior cloning and DPR learn policy directly. Learn reward function, that's IRL, access to environment. So BC does not assume access to environment. It simply takes the selection pairs from expert driving log. It does not need the environment. Interaction demos. So DPR has it. IRL does not need demos. So it's just the IRL within IRL. Pre-collected demos, yeah, except the DPR is optional. DPR can be purely interactive. So let's compare BC with DPR. So BC, the expression is argmin, the theta parameters. You're trying to optimize your policy pi theta to match the expert policy. So you assume perfect imitation so far, and then learn to continue imitating perfectly, where P star is the distribution of states visited by expert. So at every step in the learning process, you're just taking one of the selection pairs from the expert execution trace and performing a supervised learning. So so it minimizes the one-step deviation error along expert trajectories. So you can distribution is provided exogenously from expert demos. So agent is a passenger. Whereas in DPR, you are trying to sample the state from the from the next state distribution by applying a policy. Therefore, distribution depends on agent rollout based on current policy pi theta. And the loss function is the distance between the expert action for the current state and the current agent's action, the student's action. Again, you're trying to minimize the difference. Therefore, you're trying to mimic the expert. But at this time, the expert is interactive. So it can give you the pi star for any state you give it. Therefore, the agent is the driver. So agent is going along, doing the rollout, going to different states as it will, based on its own policy. And at every state, it can go ahead and ask the expert, what's your pi star? And then compare the expert pi star with my own pi theta and try to minimize the differences. So obviously, DPR is a more powerful learning paradigm than BC, but the drawback is that expert may not be always available on demand, especially if it's a human expert. So I think for the Google SureForNet, I think they collected millions of hours of drive logs by hiring many human drivers. So and then they have this BC paradigm where they only have the static logs of driver behavior, expert behavior. They don't have on-demand expert, but they did a bunch of tricks to augment the data set, adding perturbations and so on to make the data set richer. But in the end, it's still behavior cloning. So just to bring everyone to the same page, I'll introduce supervised learning a little bit because it's used in some of the papers. So supervised learning, you have two main categories. One is classification, where you're trying to predict, classify discrete labels such as a male or female, true or false, a spam or not spam, and so on. So for this example, you have two attributes, x1, x2, and you have a bunch of data points. You're trying to classify, say, a cat versus dog. So the green dots are cat pictures. Blue dots are dog pictures. These are ground truths. You're trying to make a classifier to distinguish between cat and dog. So regression is used to predict continuous values, such as price, salary, age, etc. So you have collected a bunch of X, that's the input, Y, that's the output, and you're trying to fit a curve so that you can predict for any X what is the Y value. So X may be a year, Y may be a housing price. So you're trying to predict a continuous variable. So both are supervised learning algorithms that require ground truth labels. So for the classification task, you need labels as to which picture is cat, which one is dog. For the regression, you need the actual data points. Each point is a label, that is the y-x pair, xy pair. So for both classification and regression, you need loss functions to measure the errors. So for classification, typically it's how many misclassifications. For regression is how much do predicted values differ from ground truth value. Actually, I think how many misclassifications is not very accurate. Let me rewrite it. Let's see an example. So our loss functions for classification, you have cross entropy loss, log loss, focal loss, and so on. For regression, you have L2 loss, which is mean squared error, L1 loss, which is mean absolute error. So cross entropy loss, here's an example. So you have a picture of red panda. So you have the ground truth distribution that it's a 100% red panda. So that's labeled by an expert. And your classifier, your CNN neural network, or some other classifier returns the distribution. It says, okay, I think 25% chance it's a red panda. 45% probability it's a fox. 30% probability it's a dog. So it's not very sure. It's hedging its bets. And then for this classifier, for this data point, you can compute the cross entropy loss, which is defined as a sum of I is for each data, each image, each item. So for this one, it's just 1. So Pi is the true distribution. Qi is the predicted distribution. Sorry, I is the number of classes. So, and then you can compute this loss with 0 times log 0.02, which is 0. 0 times 0 times, all of them are 0 except 1. That is this one, which is 1 times log 0.25 minus in front. So it's a 1.386. So that's the loss for this image. And then you have, say, 100 pictures, and you do an average. So as you can see, obviously, the loss is minus log qi. So the larger qi is, the smaller the loss is. In case you have a perfect classifier, suppose your classifier says 100% chance it's a red panda, then this loss will be 0. So you have a perfect 0 loss. And then if you have a very bad classifier, say a 1% chance it's a red panda, then the loss will be 100. So this cross entropy loss measures the how close your prediction is to the ground truth. So that's why I said the previous slide, how many misclassifications is not very accurate, because it's just not just counting the number of misclassifications, but to calculate how much the probabilities differ from the true distribution. So in this case, 25% and 100%, versus in another instance, maybe you have 85% versus 100%. So you need to calculate quantitatively the cross entropy loss to measure the differences. For regression, you have mean squared error or root mean squared error. Both are very common. So it's also called L2 loss. It's the average squared distance between the true target values yi and predicted values yi predicted, yp. Suppose you have n data points. So that's your MSE loss. And you can take a square root. So for example, if you make n predictions, each time the predicted value is within a minus 10,000 and plus 10,000, and suppose the true value, the expert provided label is 100, then the MSE loss is minimum 0 when yi is equal to yip equal 100, and it grows quadratically as you deviate from the true value. For L1 loss, also mean absolute error is defined as I'm sorry, it shouldn't have the square. It's defined as the sum of absolute differences between each data point prediction value and the actual ground truth. So if you plot it for that example, it's 0 at 0 and then grows linearly in each direction. So our A1 loss is more robust to outliers, but its derivatives are not continuous, making it inefficient to find a solution. Uh, uh, so, uh, so let's look at an example. So you have this data set of 5 data points, and the errors are 0, 1, -2, and so on. So the MAE, the L1 loss, is absolute value of for each item. You have 0, 1, 2, 0.5, 1.5, and error squared is and 0, 1, 4, and up to 2.25. So, but if you have outlier, say the fifth data element has a large error of 15, so the error squared goes to 225. If you take the root MSE, you get 6.79, whereas the error does not grow, error absolute value does not grow so fast. So L1 loss is more robust to outliers, whereas L2 loss is more sensitive to outliers. But L2 loss gives a closed form solution. So you can set the L2 loss derivative to 0 to find the function's max or min value. So having introduced the preliminaries, let's look at this paper. Does computer vision matter for action? So computer vision versus end-to-end. We talked about the autonomous driving pipeline. You have the modular pipeline approach versus the end-to-end approach. For if you have a computer vision as a separate perception module, it may perform tasks such as object recognition. Is it a pedestrian or a bicycle or a car or a traffic light? Depth estimation. How far away is this car from me? Optical flow. Which environment pixels are moving? Semantic segmentation. So which pixels are road surface I should drive on? So all these tasks are outputs from the perception module. So you can train a model. DNA is the most common. You can also have other models. So actually, CNN is the most common for perception. For example, you can train the model with a large data set to classify stop signs from images. So end-to-end approach is to map input images, raw pixels, directly to action, bypassing explicit computer vision tasks. Perceptual capabilities will arise as needed as a result of training for the specific task. So for example, if the training dataset is highway driving, the end-to-end model will never learn features of stop signs because there are no stop signs for highway driving. But if the training dataset is urban driving, the end-to-end model may learn features of stop signs implicitly in the intermediate layers of CNN during the process of learning the mapping from stop sign input images to braking action. But there is no explicit classification layer that outputs the label stop sign. So the end-to-end approach, essentially, it's training to learn the mapping from stop sign to braking action. You can either imitation learning or reinforcement learning. So the end goal for end-to-end approach is to map from pixel to action. It doesn't care if you have, a explicit stop. It doesn't have an explicit classification step that outputs. There's a stop sign. No, everything is implicit. So, but if you peek into the internal layers of CNN, you may see some shapes that look like stop signs, but that's implicit. So that's the main distinction between the perception module, the modular approach versus the end-to-end approach. Modular approach, you have an explicit classifier in the middle that outputs in the perception module that outputs, here's a stop sign. And then subsequently, you can do if then else, if stop sign stop. Just do a classic C programming, or you can do something else based on that piece of information. But for end-to-end approach, all you have for training is pixels and actions. All the intermediate layers are implicit. The features are implicit. So this paper reports controlled experiments that assess whether specific vision capabilities are useful in mobile sensory motor systems. So the conclusion is it is. Let me show the video.
Our planet is teeming with intelligent life. Biological creatures sense the world and move through it to survive and reproduce. And soon they may be joined by artificial creatures, robots designed to see, move, and act. How should such robots be constructed? Researchers have explored two approaches. One uses structured intermediate representations to link perception and action. These intermediate representations are produced by computer vision algorithms that perform object detection, semantic segmentation, or three-dimensional layout estimation. The intermediate representations produced by such algorithms are then used as a basis for action. This approach to building intelligent systems has thrived in the fertile plains and the soaring towers of academia. Yet it is threatened by a powerful newcomer. A vigorous species is invading from the distant lands of Neurips. This species couples perception and control directly with no intermediate representations. Pixels go in, actions come out. The new species poses a threat to older inhabitants of the fertile plains. If actions can be produced directly, what is the role of computer vision? Are intermediate representations needed at all? We study this question by training agents in simulated environments. Some agents use computer vision to build intermediate representations. Others do not. In urban driving, our agents need to move through busy city streets to reach their goal. On off-road trails, the agents ride on rough mountain roads where a wrong turn can mean an untimely end by plunging off a cliff. In battle, the agents face alien monsters in a fight for life or death. We find that agents that use computer vision are hardier. They drive better, survive longer on mountain trails, and emerge victorious in battle. Even when their vision is imperfect, agents that use intermediate representations are stronger. Here we can see agents that use computer vision to drive through city streets. And here they ride on mountain trails. When confronted by alien menace, the agents know what needs to be done. Thank you for watching.
So these are the computer vision modalities used. So A is the RGB input image, and then you can get a depth image, that is how far each object is to the camera. Surface normals is a computer graphics concept. So segmentation, that is which pixels are road surfaces, which are other cars, which is human, and instance boundaries. So you draw a boundary among each instance. Albedo is another computer graphics concept. I'm not exactly sure what. So optical flow is to detect which pixels are moving in the environment. So so all these computer vision tasks, so they compared the utility of intermediate representations for sensory motor control, that is driving or playing a video game or off-road bicycle. All these are sensory motor because they have perception and they have control. So so intermediate representations are segmentation, depth, optical flow, albedo, and they compared the performance, success rate, and weighted success rate, weighted by track length. So the conclusion is that the more computer vision intermediate representations you add, for the last one, I plus all, image plus all, you can have a better performance. Rightmost bar is the best performance. So the conclusion is that computer vision does matter. So when agents are provided with representations studied in computer vision, they achieve higher performance in sensory motor tasks. And some computer vision capabilities appear to be more impactful for mobile sensory motor operation, translation, mobile robots, than others. Specifically, depth estimation and semantic segmentation provide the highest boost in task performance. So you can imagine depth estimation tells you how far the other object is from you. Semantic segmentation tells you which is the road surface you can drive on. So obviously they are crucial to driving tasks. So my thoughts is that this result explains the rising popularity of mid-to-mid approaches compared to end-to-end approaches. So we'll have a separate perception module on the left and a separate control module on the right. And so the intermediate planning and behavior prediction are performed by the learning, by the deep neural network. So here's a paper from KAUST, a university in Saudi Arabia, and Intel Labs. It's classic. It's specifically it focuses on modular architecture. So end-to-end approaches have high sample complexity, meaning that they need a lot of training samples and difficult to scale to realistic urban driving. So simulation can help by providing a cheap training environment. And then the problem of transferring policies to the real world is same to real transfer. So you train your autonomous vehicle in the simulated environment and works well, but simulation is different from the real world. So you need to do the policy transfer. So they present approach of transferring driving policies from simulation to reality via modularity and abstraction. It's inspired by classic driving systems and aims to combine the benefits of modular architectures and end-to-end deep learning approaches. So it encapsulates the driving policy such that it's not directly exposed to raw perceptual input or low-level vehicle dynamics. And these are experiments on the real robotic truck, and it works well on 2 continents. So here's their architecture. So they have a separate perception module that takes as input a raw RGB image and outputs a segmentation map. So that is the road surface versus the rest. And the driving policy module takes this segmentation as input and produces waypoints indicating the desired local trajectory of the vehicle. So essentially, it's the job of the planner. The low-level controller, given the waypoints, generates the controls, steering, angle, and throttle. So that's the classic PID controller. So let's look at their video.
Driving policy transfer via modularity and abstraction. In this work, we train a driving policy in simulation and then deploy it in the physical world without any fine-tuning. The vehicle drives based on a segmentation map and high-level commands such as turn left at the next intersection. As a result, our driving policy is not only able to follow the lane, but is also able to take various turns based on input by a high-level planner or operator. What is more, our driving policy generalizes to various previously unseen environments. We address the problem of transfer via modularity and abstraction, combining the benefits of deep learning and classic modular pipelines for autonomous driving. Our architecture comprises 3 modules: the perception module, driving policy, and low-level controller. We first validate the system in the Carla simulator. We train the driving policy in Carla, Town 1, Weather 1. As expected, our driving policy learns to drive very well in this setting. Note that the segmentation network was trained on cityscapes and produces noisy segmentation in Carla. This is by design to allow the driving policy to generalize and learn robustness to noise. We test the driving policy in Karla, Town 2, Weather 2, a visually very different set.
So as you can see, the segmentation, the orange part is the road surface. The drivable surface is very noisy. Sometimes it's not very, it doesn't cover the road surface. So they said that it's by design. So they trained the segmentation network on a cityscape dataset and directly applied it to a Carla simulator. So it doesn't work very well, but it has benefits. Because it's not very accurate, it provides more diverse dataset and makes the driving more robust.
Setup and show good generalization performance. We then deploy our system on a robotic vehicle in diverse, real-world urban environments. Our tests include different environments and weather conditions. These include overcast weather with dry roads in Europe, but also winter weather with wet and snowy roads. We also evaluate our model on a different continent in a very different environment in sunny weather. Despite very different textures in the background, very different lighting conditions, and different road width, our driving policy generalizes well. We show that the learned policy is able to take various turns and successfully complete several routes of about 1 kilometer. Please refer to the paper for further details. While there is certainly room for further improvement, we find the driving performance very impressive, considering that this driving policy was only trained in simulation. We show that the driving policy even generalizes to a completely different time of day and is able to control the vehicle in the evening during low light conditions. Again, the driving policy is able to follow the lane and complete various turns. Please observe and enjoy the sunset. In the future, we plan to add traffic sign and object detection to stop for traffic lights, stop signs, and other vehicles, and avoid dynamic obstruction. We also plan to extend our segmentation to more classes and complement it with other representations such as depth and LiDAR. Thank you.
So the point is that not that the vehicle drives well, but the point is that they transferred a driving policy training simulation to a real truck, a robotic truck, with no fine tuning on 2 continents. So that's their contribution. So the perception module for image segmentation essentially segments the image into road and non-road regions. So abstracts away texture, lighting, shading, weather, leaving only a few factors of variation. Geometry of the road, camera pose, and shape of objects, occluding the road. So it contains sufficient information for following the road and taking turns, but it's abstract enough to support transfer. So a generalization to new environments, new weather, country, etc., or transfer to new domains, a simulation to physical world can be achieved by appropriately tuning the perception module. So it isolates the rest of the pipeline from the perception part. So as long as the perception can do segmentation, it doesn't matter if it's a lot, you know, sunny day or rainy day. So all the vehicle needs is the segmentation map. So it's an abstraction of the physical environment. The driving policy is trained with conditional imitation learning. We discussed it at the last paper in last class. So if you remember, they at each before each intersection, they have three possible options: left, right, and straight. And then the rest is just imitation learning. So for the so because so they realized that the waypoints can be so they predicted two waypoints. One is to control steering. The second can be useful for long-term maneuvers, such as controlling the throttle ahead of a turn based on this left, right, straight command. So the waypoints are encoded by the distance and relative angle with respect to the heading direction. So here you have two waypoints, W1, W2, and they are characterized by the heading angle, phi1 and phi2, and the distance to the vehicle, W norm. So, and then they fix R1, R2, that is, they fix the first waypoint to be 5 meters from the car, second waypoint to be 20 meters from the car, and a driving policy only predicts the angles of phi1 and phi2. As you can see, with the fixed length R1, R2, and the given angles, you can identify the waypoint to drive to the next. So the driving policy module is not end-to-end because it's not outputting the braking and acceleration commands directly. It's outputting the two waypoints, and it's a job of the PID controller to track the waypoints. So the expert agent, so they're not using human experts. They train the expert agent to drive based on privileged information. That is a precise map and location of the ego vehicle assumed to be known. And they have a global planner to randomly pick routes through a town and produce waypoints along the route. And PID controller is used to follow these waypoints. And then the data set of the car is randomly initialized. The car is randomly initialized within the lane, not always in the center, to record 28 hours of driving and follow the conditional IR approach and inject noise to data augmentation in 20% of the data to make the imitation learning more robust. So data augmentation, they augment the data on the raw input images. So randomly perturb the input images, brightness, saturation, hue, contrast. When training the segmentation networks, the perception module. When training the driving policy module, randomly perturb the images with Gaussian blur, additive Gaussian noise, spatial dropout, etc. So the simulation environment with different weather, different towns, and you can see the significant visual difference between the towns and weather conditions. And the performance, they compared the image to control is the end-to-end mapping from pixels to control, and image to waypoint is the into mid approach, predicting waypoints from color images. Segmentation to control is a mid to end approach. So you take the segmentation segmented image from the perception module and predicts the low-level control. And finally, this is the mid-to-mid approach, ours. So input is segmentation, output is the waypoints. And with the plus sign, it means the model is trained with data augmentation that is adding artificial noise to the input image. And the domain randomization, this one I didn't discuss. So this essentially, it deliberately tries to mess up your input image, make it look strange. So it turns out it helps to train better driving policy, driving better perception module. So the experimental result shows that the mid-to-mid approach, the blue approach, outperforms all the others. So I think this paper's main message is that so the modular pipeline has strong benefits. So just because end-to-end is sounds cool doesn't mean that you should do it. So actually the modular approach uh, with a few tricks such as data augmentation, domain randomization, and deep neural networks for each module, not end-to-end. All these combined can make the modular pipeline very effective. So I think we can take a 5-minute break. We'll come back at 4:20. Okay, I'm back. So the next paper is from ETHZ in Switzerland and Max Planck Institute in Germany. So it's a conditional affordance learning for driving in urban environments. So it's an intermediate approach, except that it replaces there's no trajectory. It replaces the trajectory with affordances. So most approaches for autonomous driving fall into one of two categories: modular pipelines that build an extensive model of the environment, and imitation learning approaches that map images directly to control output. And the third paradigm is direct perception. So it uses a neural network to learn appropriate low-dimensional intermediate representations. But existing direct perception approaches are restricted to simple highway situations, lacking the ability to navigate intersections, stop at traffic lights, or respect speed limits. So we propose a direct perception approach which maps video input to intermediate representations suitable for autonomous navigation in complex urban environments, given high-level directional inputs. Handles traffic lights and speed signs, and as well as a smooth car following. So what is affordance? Affordance is what the environment provides you. So the video input and the directional input, that's the conditional IR, the condition, are input into a neural network. It outputs affordances such as the relative angle and centerline distance and red light, true or false. And then the controller takes the affordances and computes the control commands: throttle, brake, steer. So they have 6 affordances. For discrete affordances, they have hazard stop. For example, you see a pedestrian in your way, then the hazard stop is true. Otherwise, it's false. Red traffic light, true or false. Speed sign, none, 30, 60, 90. You have 4 choices. Continuous type affordance is distance to vehicle. Air 0 to 50. Farther than 50, we don't care. It's too far away. Continuous conditional affordance is relative angle. Conditional means that it's dependent on the directional input, left, right, or straight. So relative angle and distance to center line. So in this picture, we have a affordance of hazard stop equal true due to the pedestrian. The distance to vehicle L equal to 15 meters, and speed sign equals 30. Traffic light, red traffic light equals true. So they have distilled the input image, complex image with many pixels like this, into these 6 affordances. basically a bunch of variables. So the agent takes as input the camera image and a directional command that is the straight left or right from color simulator, and the feature extractor, which is a CNN, converts the image into a feature map and stores last n feature maps in memory from the last n time steps, where n is the length of input sequence required for the perception stack. This sequence of feature maps are, together with the directional commands, and then they are exploited by the task blocks to predict affordances. The directional commands are computed by a high-level planner, such as A* or Dijkstra, in color. Basically, it tells you just before you approach an intersection which direction you are going. It helps you to make decisions. And the affordances, the 6 affordances, are the input to the controller for longitudinal and lateral control. The control commands are sent to the color simulation environment to update the simulator. So that's why I say it's an end-to-mid approach. So it's taking in the raw images and outputting the affordances, not a trajectory, but affordances. So here's the perception DNN in detail. So you have input and images in sequence. So that's what I said before. So CNN can also take into account sequence information by stacking n images together into one large stacked input. You have VGG16, a well-known CNN architecture to extract features into feature maps, and they are provided into the task blocks for computing the predictions of the affordances: header stop, true or false; red light, true or false; speed sign, which one is it, and so on. So the loss function is the cross entropy loss for classification for the discrete labels, and for mean average error for regression for the continuous labels. Mean, I think it's absolute error. And the condition D from the high-level planner acts as a switch in task blocks for relative angle and distance to center line, because if you're turning in different directions, you have 3 choices: straight, left, and right. Each one will produce a different value for the affordance, relative angle, and distance to center line. Obviously, if you're going straight, your center line is different from when you are going right. So that's dependent on your turning direction. Longitudinal control, so the order the states in descending importance from top to bottom, as indicated by color intensity. And the let's look at from the first the over limit. So if it's over limit, then they set the brake to be 0.3 times v over v star. V star is the speed limit. If it's a red light, you do a braking action. So the brake force is 0.2 times v over 30. So 0.2 instead of 0.3, because you slow down more gradually because you're supposed to see the red light from a distance, so it's not an urgent event. 30 kilometers per hour is the typical speed zone where red lights are located, so you have 30 in the denominator. Harder stop, that's when you see a pedestrian in your way, so do emergency stop. So brake is full braking equals 1. And following and cruising, there are PID controllers tuned with Ziegler-Nichols. So this is a tuning algorithm similar to a Pt2, but it's widely used in industry. And lateral control is Stanley controller, which I omit the description. So the basic distinguishing point in the control design is that it's not based on planned trajectory of waypoints as in the classic driving pipeline. It's based on affordances, the 6 affordances. Well, you can view these relative angle, distance to center line. Well, they're not really the typical trajectory. They look like trajectory. You can kind of follow the road based on this, but it's not a waypoint as we had seen before. So here's the visualization. Visualize which parts of the image the network attends to when predicting a specific affordance. So first, you see the green parts. So that's where it's looking for traffic lights. And the red is when it notices a pedestrian crossing. Then the harder stop is true. So you can see that it's actually seeing the pedestrian as soon as the shadow appears, not even the person itself. So performance evaluation, you have the modular pipeline. That's the classic computer vision plus planning plus control. And the conditional IR we discussed last time in Cordevilla's paper, reinforcement learning with A3C. So you learn about A2C. A3C is asynchronous advantage actor critique. It's supposed to be even better. A cow is the conditional affordance learning, this approach. So it turns out cow works well on most cases, especially for so the bold letters indicate the winning performance. So a cow works well for Newtown and new weather. So it has good transfer, policy transfer to different environments. Yeah, so you've been very quiet. Any questions? So this is Cordovilla, the same author that proposed the conditional imitation learning. So this paper is from University of Barcelona, KAUST, and Intel Labs. I think the last paper was written while Cordovilla was at Intel Labs. So this is the end-to-end approach. So they realized that their previous work has well-known limitations due to dataset bias and overfitting, new generalization issues due to dynamic objects and lack of a causal model and training instability. So they proposed the enhancement of their last based on their last paper. So first, they I think they changed the loss function. Okay. So here's the classic behavior cloning approach, where you collect a training data set, observation, commands. Commands are 3 commands: left, right, straight, and action uh, for the throttle, braking, and steering, and train a DNN mapping from observations and commands to actions, and minimizing the loss function. That is the difference between the DNN's output commands and the expert actions. So observation is segmentation map. Command is one of the left, straight, and right. Action is predicted waypoints. Okay, so okay, maybe it's not end-to-end. Okay, so the loss function is the R2 loss state from a state of the ground truth from expert demo, and action, the difference between action and the expert's action. So AGT is just AI, it's the same symbol. So their previous work had some limitations. So first, bias in naturalistic driving data sets. That is the the logs from expert drivers. They have either a few simple behaviors or heavy tail of complex reactions to rare events. Uh, so So either it's just very simple, normal driving, or it's a bunch of rare events that's not really useful for training the agent. So causal confusion, that is spurious correlations, cannot be distinguished from true causes in observed training demonstration pattern. So here's the inertia problem. So when an ego vehicle is stopped at the red light, the probability it stays static is overwhelming in the training data. So it creates a spurious correlation between low speed and no acceleration. So this induces excessive stopping and difficult restarting in the imitative policy. So that is when it's stopped, it has low speed, it's slowing down, and has no acceleration. So the imitation learning just learns to associate these two as a causal relationship. Therefore, it'll when it's traveling at a low speed, it may brake, perform excessive stopping. But the real cause is not low speed, it's the red traffic light. So so you can have mediated perception where you explicitly model the causal signals such as traffic lights to overcome this spurious correlation, but they underperform end-to-end learning in unconstrained environments. So because not all causes may be modeled, and errors at the perception layer are irrecoverable. So basically, if you have a separate, say, classifier that produces traffic lights red or green as output, it helps to avoid the spurious correlation problem. But these kind of modular approaches still has drawbacks compared to end-to-end learning. So high variance So Carla talked about variance. Variance means that when you are training a policy, uh, it's very sensitive to the initialization and order in which the samples are seen during training due to the non-IID distribution of training data, non-independent and identically distributed training data. So all these drawbacks, they proposed a robustified conditional IR model called CIRS. Um, so this is the original network from the 2018 paper, and this is the new network architecture. So the improvements, first, they replaced the original CNN with a ResNet, residual neural network, which is a state-of-the-art CNN for perception with a few hundred layers and very accurate for ImageNet and other benchmarks. So, and they have a speed prediction regularization, that is, they jointly train a sensory motor controller that predicts action A with a network that predicts the ego vehicle speed VP. So originally they only have this action here for the training signal, but now they added another branch for predicting the vehicle speed. And they use L1 loss instead of L2 loss, and as it's more correlated to driving performance. So they have a citation here. So it turns out people have done some studies that show L1 loss is better for driving. So they collect demonstrations from the expert game AI using privileged information to drive correctly. Privileged information means that the agent can see everything. So it knows its location, knows the map, and respects the rule of the road, and never crashes into any obstacle. So, and then they propose the new benchmark, no crash, has more tasks and metrics than the original Kala benchmark, with 25 goal-directed episodes with different maps, empty town, regular traffic, dense traffic, and so on. So they performed evaluation with the original 2018 paper, CIL, and last one I discussed conditional affordance learning, and multitask I did not discuss. And this is the new CILR with ResNet, but no speed prediction, and CILRS with both ResNet and speed prediction. So the CILRS has best performance for all these benchmarks. So yeah, so this paper, I think it's really a few minor tweaks on the original work, CIL. Yeah, so a lot of the research is incremental, so they're not proposing some brand new architecture. So they're taking the existing architecture and uh, fixing a few parts. So for example, the speed prediction regularization module so helps to overcome the spurious correlation problem. Uh, So this is another approach from UT Austin and Intel Labs. I think Intel Labs is funding the universities on this project from different universities, all collaborating with Intel Labs. So Intel is, after it acquired Mobileye in Israel, is very heavily investing in autonomous driving. So this one is interesting. So it first trains an agent that has access to privileged information. So the privileged agent cheats by observing the ground truth layout of the environment and the positions of all traffic participants. And then the second stage, the privileged agent acts as a teacher that it trains a purely vision-based sensory motor agent that is can only see the front camera view. So the resulting sensory motor agent does not have access to any privileged information and does not cheat. So it's counterintuitive, but has many benefits. I use Carla. So Carla is an open source simulator from Intel. So that's why all research from Intel uses Carla. So here's the approach. They have a privileged agent with access to information that is the map and the all the object locations, and learns the robust policy by cheating. So it does not need to see because it gets direct access to the environment state. And then the sensory motor agent, without access to privileged information, it has a image of the front camera view only, learns to imitate the privileged agent. The privileged agent is a white box and can provide high capacity on-policy supervision. So the resulting sensory motor agent does not cheat. So let's look at the video.
Vision-based driving is hard. One of the primary reasons for this is that the agent needs to learn both perception and planning, both of which are incredibly hard problems. In this paper, we split the learning problem into two steps. First, we train a privileged agent to drive on the internal state of the simulator. This privileged agent only learns to plan and does not do any perception. We feed this agent a ground truth overhead map of the world. The privileged agent sees where the other cars are, what states the traffic lights are in, where the road is, and so on. This agent sees the entire ground truth state of the simulator when it drives, and thus it cheats. In the second stage, we train a sensory motor agent that no longer has access to this internal state and no longer cheats. We do this by supervising the sensory motor agent with the privileged agent using behavior cloning. This decomposition has three key advantages. First, the privileged agent generalizes better because it acts over a very compact representation. Second, the supervision from the privileged to the sensory motor agent is stronger, as we supervise not the final output, but intermediate representations of the sensory motor agent. Finally, the privileged agent acts as a live oracle. We only need pairs of maps and images to train the sensory motor agent. This allows us to perform on-policy training where the privileged agent is actively queried. This two-stage approach works well in practice. It solves the Coral 17 Carla benchmark and gets 100% success rate on all tasks in the full generalization setting in new town and new weather. Even on the harder no crash benchmark, it solves the empty benchmark and outperforms state-of-the-art on regular and dense traffic settings as well.
So their comparison is to a CIR, the 2018 paper on conditional imitation learning, CAR, the conditional avoidance learning I just discussed, and CIRS, the enhanced CIR I just discussed.
Settings as well. We thank you for your attention. We'll now show you Some examples of our agent drive in an unseen test town.
So it just shows that it drives pretty well. In rain, so why does it work? So the effectiveness of this decomposition is counterintuitive. So if direct IR from expert trajectories to vision-based driving is hard, why is the decomposition of the learning process into two stages, both of which perform imitation any better? So the reason is that first, the privileged agent operates on a compact intermediate representation of the environment, that is the map and its location, and all the other objects' locations. Thus, it can learn faster and generalize better. So it has the bird's eye view, enables simple and effective data augmentation, and facilitates generalization. So second, the trained agent, a privileged agent, can perform much stronger supervision than the original expert trajectories. It can be queried from any state of the environment, not only states that were visited in the original trajectories. So it turns passive expert trajectories into an online agent that can provide adaptive on-policy supervision. So it's actually, I think it's actually we discussed this DPR, dynamic direct policy learning. So essentially, it turns into a direct policy learning problem. And third, if the privileged agent is trained via conditional imitation learning, it can provide an action for every possible command, left, right, straight, all at once in any state of the environment. So it can train all branches of the sensory motor agent in parallel. So in every state during training, the agent, a student can ask the privileged teacher, what would you do if you had to turn left? What would you do if you had to turn right here? And so on. So my analogy is that expert driver is like a Kung Fu master who lives in the mountains, provides recorded video lectures, but is not available for interactive instructions. Where the privileged agent is a student with perfect eyesight because it's cheating, right? It's given the map of the environment and every object in it with bird's eye view. Hence, can learn effectively from the master, but the sensory motor agent is a young pupil with poor eyesight, with front camera view, who can learn more effectively from the junior master, from the privileged agent, with interactive instructions than from the master directly. Yeah, just a analogy, just a young student may learn better from a graduate student who can provide detailed interactive instruction than from a senior, very old and established professor, right? So the agent architecture, so the privileged agent receives the bird's eye view of the environment, bird's eye view of the environment here, and produces, the CNN produces a set of heat maps and goes through a soft argmax layer to yield waypoints for all commands. And then the input command C selects one conditional branch, and the waypoints are given to a low-level controller that outputs the steering, throttle, and brake. And the sensory motor agent receives a genuine sensory input, that's the front camera view, and produces waypoints in the egocentric camera frame. And waypoints are selected based on the command projected into the vehicle's coordinate frame and passed to a low-level controller. Okay. And the loss function, so a privileged agent tries to imitate the expert by minimizing this loss function here. Minimum of the ground truth trajectory and its predicted trajectory with L1 loss. And sensory motor agent tries to imitate the privileged agent by minimizing the expected difference between the own predicted trajectory and the by privileged agent. So that's its predicted trajectory. That's the privileged agent's predicted trajectory. So therefore, the sampling is no longer restricted to the offline trajectories provided by the original expert. So the learning algorithm can sample states adaptively by rolling out the sensory motor agent during training. It can be supervised on all its waypoints and across all commands C at once. So yeah, coming back to here, the so the here's the W is the ground truth, the expert predicted trajectory. That's the W. And the heat map from the CNN is the F theta star, the agent produced trajectory. And their difference, L1 difference, is the loss function. Here, the heat map is F from the CNN output, and the F theta star is the privileged agent output. So you can see that it's a middleman in the middle, right? So you're learning from the privileged agent, which learns from the mimics the expert. It turns out this middleman approach actually works better than mimicking directly the expert. And data augmentation, this is the old trick we saw many times. Basically, you tweak the input data set, make it rotate, and move shift the different cars in different positions to try to make the data set input data more diverse. And the controller is the low-level controller is longitudinal PID control and lateral PID control. So longitudinal just tries to track the target velocity, that is the difference between two neighboring waypoints divided by delta t, the temporal spacing, the time step size. And lateral PID controller tries to match the target heading angle from to the waypoint. So so to overcome the noise issue, that is the predicted waypoint may not be very accurate. It may be noisy. So they fit a curve this curve based on the waypoints. So it's a smooth arc to average out prediction error on individual waypoints. And then you project one of the predicted waypoints onto the arc. And you for straight and follow the road commands, you use the W2, the second waypoint, shown in the figure. For right turn, you'll use the third waypoint, and W4 for the fourth waypoint for left turn. The larger waypoints allow for a larger turning radius. So the paper uses the term steering angle, but it's actually the heading angle. If you recall, the steering angle delta is different from the vehicle heading. There's a relationship, but it's indirect. The performance evaluation compared to the previous conditional imitation learning. This one I didn't discuss. Conditional affordance learning, conditional imitation learning enhanced. They have a better performance. So this group from Intel Labs and their collaborating universities, this series of work on imitation learning and their enhancements are representative. They are widely cited work on imitation learning for autonomous driving. So that's why I picked out these papers to discuss, because their work is pretty representative of current research front. So I think we are out of time. I think Carla will not give any more lectures from next week on. So I will give lectures starting from 1 o'clock. So I may have to send out a new Zoom link. So as far as lecture content is concerned, so in the past 2 weeks, I have been discussing research papers. So Carla has been discussing the fundamentals. So I will kind of pick up where Carla left off to discuss more basic knowledge on reinforcement learning, imitation learning, and related approaches, and combined with discussions on research papers. So hopefully it's okay. And if you have any comments and suggestions as to how the future content should be taught, just leave me a message. So I have put this link on the Canvas in the last have a feedback form. You can use it throughout the semester anytime. Okay, any questions on today's material? Yeah, so one last thing. So I think most of you did not really do anything more on the assignments. So I left, yeah, cannot find DT in this Python. Please clarify. So did not call robot move and so on. So but it did not respond. Yeah, so I mean, if you're not, if you don't really have time for this assignment, I mean, that's fine. But if you don't respond, and it means that what I said is true, so I will take some points off your assignment. So how much off, I'll decide later.
But if you have given a grade, then it stays that way, right?
Well, I may change it later because so many people did not do the second part. So I may reduce the weight of that part a little bit.
Okay.
Yeah, we'll see.
But because I did the second part, but I got some comments. Not really. I don't think you said anything was really wrong, but you had some. I don't really remember right now what you said, but you had some comments, but you gave me a grade. So I mean, will that stick, or I mean, if you graded it, do you expect any answer to the comments?
I see. Yeah, I have a few comments. Yeah, one little thing is that the PID gains are ordered PDI.
Yeah, I saw that. I was just wondering. I read your comment, but I was wondering if you were expecting like an answer or not.
Actually, it's yeah, it's not a big deal, so you don't have to answer. I think it's fine. Your assignment is fine.
Okay.
Yeah. Okay, so see you next week. Have a nice weekend.
Yeah.
Goodbye.